Uh, I have the unpleasant duty of starting with all the boring stuff this morning, so I thought we'd get off with the quick review of mass spectrometry and all the the basic terms and concepts. It does get more interesting after that, so bear with me for a little bit. Some of this will probably be review to some of you, but I just want to make sure everybody gets off on the same page here. So let's see. There we go. Here's the outline of what I want to talk about. Just start with a definition of terms, then review how DART works. We're going to start with the basics of how DART works, and then later I'll come back and talk about some of the subtle, less obvious things about how it works and how the harder samples are managed. I do want to talk about the time-of-flight mass spectrometer because we're working with time-of-flight mass analyzer in the lab. So I want you to understand what the information is that you get from the instrument itself and what we can do with that information. We're going to be using exact mass measurements to confirm knowns and to determine elemental compositions for unknowns. So I want to talk a little bit about the basic concepts of high-resolution mass spectrometry. In particular, things like resolving power, which tells you how narrow your peaks are and tells you what you can separate from interferences. And talk a little bit about the elemental composition software and how that works. We'll be doing more of that in the lab, so some of this will be a whole lot more obvious when we get done with it. But there's a lot of information that comes along with the elemental compositions that helps you to try to interpret what you're looking at. So we need to think about some of that. Resolving power is a definition of how narrow the peaks are in a mass spectrometer, and it's defined as the mass that you're measuring at divided by the difference in masses that can be separated at some definition. I don't think the pointer is working. No, that one's dead. Let's take a look. Here's an example of resolving power defined as full width at half maximum, which is what the definition that's used on the time-of-flight mass spectrometer. So if resolving power is m over delta m, let's say we have a resolving power of 5,000 at mass 500. In that case, then, the peak width at half height would have to be 0.1 mass units. If we take the same definition, same units, let's say resolving power of 5,000, and we have, no, I'm sorry, resolving power of 500, then that means that mass 500 and 501 can be separated. So in this case, the 10% valley definition just means that there is a valley of 10% between the two peaks, and you can separate mass 500 and 501. Here's the same mass done at two different resolving powers. This is really hexatriacontane, but it's close enough to mass 500 that you can extrapolate. On the left, you see a resolving power of 500 with a 10% valley definition. So that means that mass 500 and 501 can be separated from each other. With resolving power of 5,000, you can separate mass 500 from mass 500.1. So see how much narrower the peaks are. The Akutov resolving power is going to be awfully close to that. And just to avoid confusion, you'll hear people say resolution sometimes. If you want to be nitpicky, resolution is the reciprocal of resolving power. So the correct term for talking about this is actually resolving power. It really won't affect your measurements, but that's the right term to use. Now, it's worth pointing out that even if you're only separating things that are a tenth of a mass unit apart, we can actually determine the exact mass of these things to 3 or 4 decimal places. The reason is that you use all the data points on the peak to determine the exact center of the peak. So even though the difference in mass is only 0.1, the accurate number that you can measure is 3 or 4 decimal places, as long as there's not an interfering peak present. So if you have nice clean peaks like this, we'll be reporting 3 or 4 decimal places. Here's why the definition matters. You can define resolving power lots of different ways. You can talk about resolving power at half height, the width of a peak at half height, or you can talk about the different, how low a value you can get between two partially resolved peaks. Here's the same example again done with three different definitions. We're assuming resolving power 500. 10% value definition, you can see the peaks are pretty well separated. They're not completely separated, but they're clear and distinct. If you use the half-height definition, peaks aren't very well resolved. I mean, the peaks are they're 1 mass unit wide at half height. So when you've got two things that are adjacent, you can't really tell the peaks apart. The lines are where the masses actually are, and the red trace is what the instrument would measure. And finally, with the resolving power 5,000, you can see things are nice and cleanly separated there. So the Akutov is going to have a resolving power of about 6,000 at mass 600. So it's going to be a little better than this, and you can see why this will be helpful. We'll see examples in the lab of peaks that have the same integer mass but actually differ a lot in exact mass. When we talk about mass accuracy, there are a couple of different ways to refer to it. I like to use millimass units, which is just the third decimal place. It's very simple. Just millimass unit is 0.001 mass unit. And before I go on further, I should just remind everybody that in mass spectrometers, we're talking not about mass, but we're really talking about mass to charge ratio. In DART, you're only going to have one charge on all the peaks. You never have more than one charge. So technically, we are looking at mass, but we should be correct about that. If you use electrospray or some of the other techniques, you can often have a charge that's not 1. And so the mass spectrometer is measuring m over z, or mass to charge ratio. Okay, so millimass units are easy. It's just, 5 millimass units is 0.005. 10 millimass units would be 0.01. But a lot of the journals use parts per million as a mass accuracy definition. And that's really because parts per million is resolution. It's the reciprocal of resolving power. I don't particularly like that definition, but it is the definition that a lot of people use. So see, it's the reciprocal of resolving power. Resolving power is m over delta m. ppm is delta m over m. But because it's such a small number, you multiply it by 10 to the 6 to give you a part per million value. Now, the reason I don't like that is that you've got an m in the denominator, and parts per million, then if you think about it, if you've got a low m, a small mass, then that's a really small number. You have to have a really tiny part per million value. Well, at low masses, there aren't very many possible combinations of atoms that will give you a given mass. So you don't really need really high resolving power at low mass. You don't really need extreme accuracy at mass 18. At mass 18, you're just going to have 18.01 or 18.03. And at high mass, because this is in the denominator, you've got a large number in the denominator, you've got a really tiny value. So you can have really sloppy mass accuracy at high mass and still get a good ppm value. So that's my personal opinion about this. Nevertheless, the software will let you calculate both kinds of numbers. We'll see examples of that in a little bit. The software for elemental compositions will also give you other information. We'll talk about unsaturation, which is the rings and double bonds in a given composition. And this information is also useful in trying to understand what you're looking at, so it's worth pointing out. Let's just take a look at a couple of examples. Benzene on the left, if you have the benzene molecular ion, you have one ring and 3 double bonds, so the unsaturation index is going to be 4.0. There's a fractional part that tells you whether you have an even or an odd electron ion. And this value is actually calculated from the elemental composition and knowing the valence of each of the atoms. There's a formula, I don't know if it's on one of these slides or not, but I'll show you a reference later where you can look it up if you're curious. But it just shows you the total number of bonds. So triple bond counts as 2, a ring counts as 1, a single bond counts as 1. You add all those up and you get a number. But sometimes you get things that aren't neutral molecules. So you have an extra proton on most positive ion species in DART. And so then you wind up with a half integer calculated number. You're not working with just a simple valence right off the periodic table. So let's take protonated acetone here. You've got an extra proton attached to the oxygen on the acetone. You calculate unsaturation index of 0.5. that tells you that it's an even electron ion. And if you have a positive ion, think positive, you have to add 0.5 to find the number of rings and double bonds in it. So if it's positive, think adding 0.5. If it's negative, think subtracting 0.5. And so you can see we've got one double bond in there. If the software says 0.5 for the unsaturation index, add 0.5, and that's the number of double bonds. That'll be 1. Here's acetic acid. The unsaturation index comes up as 1.5, but it's negative. So you subtract 0.5, and then you have the one double bond in the acid group. And then you have protonated water, which is hypervalent. That actually comes out as minus 0.5, and you have to add 0.5 to realize that you have 0 rings and double bonds in the protonated water. So by default, the limits that you put on possible compositions allow you to specify the number of rings and double bonds in a molecule. And you'll see that the default value is below 0. This is the reason. There's one more thing. If you have non-covalent complexes, then the number can even go more negative because you don't really have, well, you don't have just standard valence for that sort of thing. Okay, so here are some examples of even electron ions and odd electron ions. Even electron ions have an unsaturation index with a half integer, so it'll end in a 0.5. So you take a protonated molecule, which is the most common species in positive ion DART spectra, and that will end up in 0.5. A deprotonated molecule is the most common species in a negative ion DART spectrum. You might wind up with chloride adducts for explosives, or ammoniated molecules for ethers, or a fragment that is formed in DART. So almost all of these things will wind up with a half integer rings and double bonds value. Odd electron ions have an exact integer, like 4.0 or 3.0, and those refer to things like a molecular radical cation or molecular radical anion, or some odd electron fragments. These kinds of things are more common in EI mass spectra and GCMS, but you will see them in DART sometimes. We'll talk about the mechanism later. Sometimes you'll see molecular ions for certain kinds of compounds, or you'll see pairs with peaks like that. So it's worth remembering that these things can happen even though they aren't very common. Here's some online resources. We have a DART users Google News group. We've got about 150 members right now. It's a private news group, but anybody using DART or interested in working with DART is certainly welcome to join. I kept it a private news group just to keep the internet crazies out, and so far it's been a really productive resource. So if anybody's interested, you can either let me know and I can send you an invitation, or you can go online on this and just request an invitation. The Joel USA Incorporated web pages do have a lot of information about DART. All of the application notes are there. News appears sometimes. We've got tutorials and reference materials, some of which are in your notes. But don't go to jeol.com. Go to jeolusa.com. The jeol.com link got hijacked by the parent company in Japan. If you go there, it says you have to register information, and it doesn't have the same information we do on the local website. But if you go here, you can get right in, and all the information is there under the product pages. Likewise, IonSense is the company that makes the DART. It's a spin-off company from Joel USA. It's a wholly U.S. company. It's independent from Joel Limited, which is a Japanese company. And so IonSense primarily makes the DART, but they're also working on some other things. There's some data processing software and DART sampling devices, and it's really a path forward for high throughput development centered around DART. There is a Wikipedia article on DART. It's got some public domain figures that you can use if you ever need a schematic or a couple of examples on there. It is Wikipedia. So far, it's maintained its integrity pretty well. Nobody's really tampered with it very much, so I think it's a pretty good resource. And finally, we talk about proton attachment and ionization and things like that. If you want to get down to the nitty-gritty, the NIST website has a really good resource for ion information, ion thermochemistry and gas phase ion energetics and things like that. So if you want to look up proton affinities or ionization energies or anything like that, you can go to the NIST web book and you can type in compounds. They can show you mass spectra. They've got IR spectra. It's a very nice public resource. Obviously, not everything is in there, but often if you can't find a compound you're looking for, you can find something similar to it and take a look. So if I want to know whether something will be protonated by water in DART, I can go look up its ionization, its proton affinity on the web and try to figure out whether it's got a higher proton affinity than water or not. That's going to be a good guide about whether something will work in DART or not. It's worth checking those links out. Normally during a training class I'd click on each of those and show you what each page looks like, but it's a little awkward to do that right now. So I just recommend if you get a chance, take a look at the links sometime just to see what they look like. Now let's get to the core of this and talk about the basic principles of DART. There is a Joel News article online. I think it's also in your handouts, but it was an article that it's a public domain, non-copyrighted article that you can use that has all of the basic information about DART, a lot of which was in the original analytical chemistry article. And so that's another good resource for reviewing some of this. Here's the history. DART came out of discussions between myself and Jim Laramie, as a friend of mine from grad school, about how to make an atmospheric pressure electron monochromator. We actually wound up building something that turned out to be a lot more powerful than that. But it was actually, we started talking about this in 2001. We built something in 2002 that wasn't quite what we thought it was going to be. It turned out to be much better. And by January 2003, we had a working DART. And we first announced the DART at the Sanibel ASMS conference I think it was in Clearwater, Florida that year, which was in January 2005. And that's where I first met Bob and heard him give a very entertaining talk. We published an article in Analytical Chemistry shortly thereafter and went to the Pittsburgh Conference of Analytical Chemistry and Applied Spectroscopy and had the commercial DART fully implemented, ready to go. So that was March 2005. DART and desorption electrospray ionization both were publicly announced about the same time. The DESI article from Purdue came out just before 2005, but I do think DART was first because we actually had it working in January 2003 and had the patent filed in April 2003. The two techniques, we can talk about them at another time. I think they're complementary, really. They're not exactly the same sort of thing. Here are some references for you. Here are the two patents. I think the articles will be listed in a bibliography. The patent came out, it was actually issued in September 2005, and then there was a subsequent one that came out a year later. Here's what the original ones look like, just in case you're wondering. We really envisioned this thing of being a gas phase thing, so we built this little thing on a stand and hooked it up to a meter and started squirting gas in it with a gas-tight syringe, and it looked like the picture on the left. It gave us all kinds of interesting readings that we didn't understand. We kept making graphs with Excel and plotting them out and didn't really know what was going on. So I said, we've got to figure out what's going on in this thing. So we took one of the end caps off and pointed it at a mass spectrometer, and that's when all the fun started. Here's a generation 2 prototype that was, again, just followed this thing. This was probably in the middle of 2002 before we really understood what it did on the left. This was a little later. And it was made out of a GC injector liner. So you can see it's actually pretty small. The blue can that you see is mostly insulation and protection against high voltage. So the DART itself doesn't have to be very large. This one was made of a clear plastic, so you could actually see the glow discharge inside the chamber. It makes it really interesting to see what's going on there. And you can see this was on a stand, so it could be pointed at any angle at a surface. The current commercial version is a fixed direction DART pointing straight at the orifice. IonSense has just introduced a variation on that allows you to set the DART at an angle and bounce the gas stream off a surface, and has a pickup tube. I can try to show you some of that a little later. But just for the historical interest, that's what it looks like. I've still got that one in a drawer someplace. I don't know what happened to this one. Now let's talk about how the DART looks like in context on the mass spectrometer. You'll see this in the lab, but the Accutop's about the size of a washing machine. It's pretty much self-contained. You'll see in the lab that the rough pumps are inside the cabinet and the whole thing's on casters. From over here, the aspect ratio makes it look a little narrower than it really is, but you'll see what it looks like in the lab for real. The dart source is the blue can on top, and the flight tube for the mass spectrometer is a vertical 1 meter stainless steel can about this big in the back of the mass spectrometer. Okay, why bother to worry about things like DART? Well, it really is fast and easy. It's the most fun I've had since I started doing mass spec years ago. We came close back in the 80s when we got laser desorption working on a Fourier transform mass spec, and we started putting everything we could find into that. But this is even better because you don't have to put samples in a vacuum. Most samples don't require very much sample preparation, but some sample preparation is very helpful for many samples. If you can do something that's fast and easy to make your samples work better, then it's well worth it. I know Peter will talk about some of that. I'll talk a little bit about sample prep too, but there are many samples we can run without any sample prep, and that's convenient. The DART can tolerate dirty samples. We really have run mud and blood and urine and just about everything we can find, wipes off the bottom of the shoes and melted plastic. I like running peanut butter and chocolate as demo samples because you couldn't do that in an ordinary mass spec without messing things up. And it is really good for fast fingerprinting of materials. We'll talk more about what kind of information we get for that, but it is really nice to be able to just stick something in front of a machine and get some kind of information. Nothing comes without a price. There is no perfect mass analyzer, there's no perfect ion source, there's no perfect ideal analytical instrument. If you throw away the chromatography part of the chromatography mass spec, you are throwing away information. If you do GCMS and LCMS, those techniques are so highly refined that they're still way better than trying to do this without any chromatography. We're trading convenience and broad applicability for sensitivity and specificity for certain analyses. DART is no good for large biomolecules. You can't do proteins or DNA fragments with it. That's still best done by things like electrospray and laser desorption. And DART doesn't ionize metals or minerals. I'll show you a trick where you can get some of that information kind of indirectly, but these are the things that DART doesn't do very well. Okay, finally get down to how it works. This is the simplest thing. We were really shocked that nobody else had done this, but going back through all the prior art when we filed the patent, we found that a lot of people had headed right in that direction, and right before they got to where we were with DART, they took a left or a right and went off in a different direction with it. Essentially, we've got a tube with some electrodes in it. On the left, you see a glow discharge chamber. So we're blowing some typically helium or nitrogen through a tube. We've got a needle that's a high voltage, usually about 3,500 volts. There's a counter electrode at ground. And if you blow a gas through those and put a potential on the needle, you get a glow discharge. And it is a glow discharge because it lights up like a neon light in there. It's really quite pretty to look at. But the glow discharge contains a lot of species. You've got positive ions, you've got negative ions, you've got electrons, you've got all these highly excited, very short-lived species like helium-2+ and helium-2 star in excited state. These things don't survive very long at all. They only exist in the glow in there. But a few things do survive. Some ions survive. Most of those are lost in passing through the subsequent electrodes. And essentially we wind up with only excited state neutrals coming out of the DART. So again, we've got a needle and a counter electrode, which is at ground. You have a potential that you can control for the needle. It's one of the parameters. The ground is grounded. There's no potential for that. There's an intermediate electrode, which helps to get rid of some of the charged particles, but frankly, its potential doesn't affect the spectra very much. So we call that electrode 1. I think in the IonSense software they call that the discharge electrode, which is a little confusing because it isn't involved in the discharge. I've suggested they change the term to something else. The important one is a grid at the end here. And That's also a lucky accident in some ways, because we were trying to measure the current at some of the different points. I didn't want to just pull the electrode out when we took the end cap off, so we stuck some aluminum foil over the prototype and punched holes with it in a pin. It turned out the grid electrode is actually very important. I'll explain why in just a minute. So the gas blows through this grid electrode, and the grid is either positive for positive ions or negative for negative ions. And then out in this region, you get excited state atoms coming out to interact with the sample and produce ions that then are blown through the hole into the vacuum part of the mass spectrometer through a little orifice here. Here are the 3 steps in a schematic, and both of these figures are the ones that we put on Wikipedia. The first step is pending ionization. We'll break these down one by one and do them in detail in just a minute. But pending ionization is when you have a neutral molecule that interacts to produce an ion with another material. It's called chemionization when you start with a neutral and you wind up with an ion. And pending ionization goes back to a paper from F.W. Penning in 1927. It was about a half-page article in German that was published in a physics journal, where they found out that excited state argon could produce ions from other gases. So we talk about these as being metastables because they're long-lived excited state neutrals. The helium metastable that we work with in a vacuum will last for about 8 minutes before it transfers its energy to something else. So that's a really long lifetime. But in practice, the metastable will stay in excited state neutral until it bumps into something, whether it's another gas molecule or a surface or something like that. In most cases, the helium ionizes atmospheric moisture, and it's a really efficient reaction. And then the ionized water clusters will transfer a proton to the sample. We'll break each of these down step by step. So you wind up with an M plus H plus most of the time. In negative ion mode, you still start with a pending ionization, but the pending ionization produces a positive ion and an electron. It's the electrons that are the important part of the first step in making negative ions, and those ionize atmospheric oxygen. And then the atmospheric oxygen reacts with the sample to produce ions. So breaking this down step by step, here's the pending ionization step. The metastable excited state neutral atoms or molecules react with the sample. The sample has to have a lower ionization energy than the internal energy of the excited state. And the helium triplet state that we're working with has an internal energy of about 19.8 electron volts, which is pretty much higher than almost anything you're going to encounter. To give you a reference, things like benzene have an ionization energy of about 8.5 electron volts. Most organic molecules are about 12 electron volts or higher, but certainly not almost 20 electron volts like the excited state helium. So the first step will be the excited state reacting with a sample to produce a positive ion and an electron. This is okay. In positive ion mode, then, the next step is this. The reactions aren't really important to being able to use DART, but you might as well know what's going on so you can appreciate things when you see them. The helium triplet state then reacts with water to produce water ions, and those water ions react with other water molecules to make protonated water clusters. So you wind up with this kind of thing. This reacts with your sample to give you a M plus H plus and water. This is a really, really efficient reaction. So we had a lot of questions about what happens when you do this in the desert. We've got customers out in parts of Utah where the humidity is really low. If you're in the room and breathing, that's enough water for this reaction to happen. We read a Dutch graduate thesis where they looked at reactions of cold metastable helium atoms in high vacuum, and they decided to see what the mass spectrum looked like. At 10 to minus 10th torr in an ultra-high vacuum, all they could see was water ions. So the water was just coming somewhere off the wall, even at that incredibly high vacuum. So that tells you how efficient this reaction is. So you really don't have to worry about whether it's a humid environment or a dry environment. This is going to work. Okay, here's a typical low mass background. I'll come back to this in my second talk tomorrow. But One of the nice things about the time of flight mass spec is that we can see some of these low mass ions, so we can actually see what's going on that's causing these reactions to happen. You'll see this if you set one of the parameters low, so you can see low mass ions. And it's one of the things you do when you check to see whether the dart's working or not. You want to look at the background to make sure that it looks something like this. So at the low mass region, you'll see NH4 plus, which is at mass 18.03. That's ammonium. In my lab, the ammonium's there because I put it there, but you will find it there even if you don't put it there. I guess humans emit ammonia, and there's ammonia present all over the place in the background. So don't be surprised if you see it there and you didn't put it there deliberately. You also see H3O plus, which is protonated water, and you'll see some other species, a little bit of methanol there, some oxygen, a little bit of NO plus, which will become important later, water trimer. But the important thing is this mass 37 peak should be really strong. And this is a good background because you see a really strong 37 peak and you see a really low background. If the machine isn't working badly, then you'll see a really noisy background and a weak 37 peak. So I'll show you when we get to the lab part about how to check this to make sure it's working. But mostly we just get this water dimer, and that is what's going to react with the samples. Okay, let's flip polarity and talk about negative ions. The first step in the pending ionization, you remember, makes a positive ion and an electron. In negative ion mode, the electron is the important part. And here's where the grid comes in. If you remember, we're making both positive and negative species at the first step of ionization. Well, if you just leave them alone, they're going to combine and give you a neutral, and you don't wind up with any ion current. So if you've got the grid at plus 250 volts, then all of the electrons are going to get sucked back to the grid and removed from this, and so they can't recombine with the positive ions that are formed, and so you have efficient positive ion formation. If you're in a negative ion mode, any positive ions that are formed are going to get pulled back to minus 250 volts, and so you're left with just electrons coming out. So the grid helps to define the polarity by getting rid of the opposite charges from the ones you want to look at. Okay, so the first step then, you have electron that's either produced when the metastable hits a negatively charged grid. You can make electrons just from a surface. Or if the metastable strike a gas molecule and make a positive ion electron, you pull out the positive ions, you're just left with the electrons. So then the electrons have different energies. For electron capture to happen, you have to have a very specific energy. It's close to zero. The electrons almost have to be at a standstill. But they bump into a gas molecule right away, whatever their energy is, and that's going to slow them down to a dead stop. It's like shooting BBs into a swimming pool. They're going to lose their energy right away and just be drifting along. So those slow electrons are picked up by the oxygen, and you wind up with an O2 minus dot molecule, and that can react with the sample in three ways. The most important one is that it can pull a proton off of a molecule, so you wind up with an S minus H minus. And you also get some radicals here, which can oxidize samples. If you have to be aware that that's possible. You can get just direct charge transfer, where you transfer the electron from one molecule to another. You don't see that very often, but it can happen sometimes. And you can also get oxygen attachment. So negative ion mode, you might see something plus O2 minus. For example, hydrogen peroxide gives you H2O4 minus. You get hydrogen peroxide plus O2 minus. This is the most important one, and most of the time you'll see M minus H minus. You can also get fragmentation from some of these, and we'll talk about that a little later. Here's a typical low mass background. You will see, in addition to the oxygen, you can see things that involve water and CO2. The ratios of these depend a little bit on the parameters, but they're not really critical in determining whether DART is going to work or not in negative ion mode. What is important is that you don't see a lot of NO2 and NO3, and those would happen at mass 46 and mass 62. If you just do a glow discharge out in open air, pretty much all you see is NO2 and NO3. And corona discharges are used for some of the explosives detection devices, the ion mobility devices. And this has been a real problem because if you use a radioactive ion source, you don't make much NO2 and NO3, but then you make a corona discharge, you get gobs of NO2 and NO3. Well, first of all, that's no good if you want to look for nitrates. You want to know if you've got explosives present. You want to look for those species. And secondly, these things interfere with the formation of more characteristic ions. So it's really good that we don't see much of those things. If you see too much 46 and 62, that means you've got too much oxygen in the gas that's blowing through the dart. So if you were to take nitrogen from a nitrogen generator and blow it through there, you just might see a huge 62 peak because nitrogen from a nitrogen generator has about 0.3% oxygen in it. This is a good spectrum because you don't see those things, not to any appreciable extent anyway. There might be a trace of 62 there, there's a little trace of 46 there, but not so bad. Okay, so here's an ideal example. Here's ascorbic acid. We were interested in this too because apparently it's in smokeless powders, and there are problems in trying to detect it for various reasons. But in an ideal case here anyway, a positive ion, ascorbic acid is an acid. It really wants to be a negative ion, but this is one of those few molecules that will form an M+H+ in positive ion mode. But you also see dehydration peaks. The higher the temperature of the gas that you're using, the more likely you are to see decomposition. But this really doesn't want to be a positive ion very much, so you start to see these things. Some other acids won't ionize very well at all in positive mode this way. Aspirin's an example. But in negative ion mode, you get a nice M-H-, and you actually get a little bit of molecular ion as well. So there's an ideal case. You get a positive and negative ion from each of those. And this is just dipping a glass melting point tube into some ascorbic acid and waving it in front of the dart. Okay, we'll talk about more complex spectra in a little bit, but let's explain how the time of flight works so you can get that out of the way and move on to the fun stuff. Once again, there's a Joel News article on this, and it's a really nice, definitive article. It's not an advertising article. It tells you in great, gory detail how they chose the different components for the time of flight and how each part of it works. There are different kinds of mass specs, and you can put DART on different kinds of mass spectrometers. I think it's important to understand what the pros and cons are for each. We're working with the time of flight, but it is possible to put a DART on everything else except a magnetic sector mass spec. The only reason for that is that magnetic sector mass specs have an ion source that's at high voltage, and there's no point in having an open air source if it's all sitting out at high voltage. But you can put these on scanning mass spectrometers like quadrupoles and triple quadrupole mass spectrometers. DART has been put on all of the trapped ion kinds of mass specs, and it's also put on hybrid combination type systems where you combine one of these with something else. Scanning mass spectrometers, you scan the observed mass over time, and one of the problems with that is that DART allows you to desorb and ionize things very quickly. Sometimes processes can happen quickly. So the time of flight's really good because you get a snapshot just in an instant of the entire mass spectrum. You don't have the problem that your ion current is changing while you're trying to scan across a peak. If you're using a scanning mass spectrometer like a quadrupole or a triple quad, they really work best with selected ion monitoring where you're just jumping from one kind of mass to another or one kind of reaction to another. If you try, or you have to scan very fast so you don't lose something while the ion current's changing. We have seen some really nice data from triple quadrupole mass specs for target compound quantitation, where if you decide in advance what you want to look for and you just want to know how much is there, you look at an MS-MS reaction, for example, that's characteristic for that compound, and then just plot out the trace. Ion traps work. You can put a DART on an ion trap. You do get spectra, but they aren't very good for quantitative analysis. And the time of flight is really the fastest mass spec for transient detection. It gives high-resolution data for the entire mass spec with no sensitivity loss, at least talking about the analyzer. So it's really good for characterizing what's there. I think the triple quads or some of the hybrids might be really good for trace quantitative analysis of some of these compounds in a complex mixture. So we'll be focusing on this one. I like bicycle racing, so I'll try to explain time of flight in simple terms. Worth mentioning that the Ragbri ride just came through Ames just a few weeks ago. Thousands of people on bicycles passing across the state of Iowa. Anyway, if you start at the bottom of the hill, and let's say you have everybody's equally strong, but you have a heavy rider and a light rider. Going up the hill, the lightest rider is always going to get to the top fastest, and that's the the hand-waving explanation about how time of flight works. So the point is everybody starts at the same time, has the same kinetic energy. The lighter particles are going to reach the detector faster. More realistic time of flight is like this. Here you've got a vacuum flight tube, and you've got an ion source at the beginning, and usually you have a burst of ions either from a laser desorption pulse, or you form the ions some other way and you open a gate momentarily just to let a burst of ions into the flight tube. The ions are accelerated across a potential difference, say from 0 to several kilovolts there, and so they're all given the same kinetic energy. Kinetic energy is 1/2 mv squared, but for charged particles, kinetic energy is just charge times the electric field. So if everything has the same charge, everything that leaves the ion source has exactly the same kinetic energy, but if the masses are different, the velocities have to be different to keep this constant. So the light ones get to the end first. So you do the pulse, you let the ions go through the flight tube, and then you have sort of a fast digital stopwatch on the other end and count when the ions arrive. Well, this isn't perfect because some of the ions might start at the back of the ion source, some of them might start at the front of the ion source. There might be other reasons why they don't have exactly the same kinetic energies, even though they have different masses. So one of the tricks that came up in the 1980s from a Russian named Momirin is called reflectron, where you bounce the ions into a tube, turn them around, and bring them back out the other side. So you make the more energetic ions go faster than the less energetic ions, and they all catch up at one place. Well, go back to the bicycle race. This actually happened to me, and I was the only guy geeky enough in the bike race to actually think of this as a reflectron while we were pedaling as fast as we can. But here we are headed toward a turn. Lance wasn't actually in the race, but that's all right. We were supposed to turn here. The fast guys were pedaling so hard that they didn't realize they were supposed to turn. They headed down before they saw the stoplight and realized they had to turn around. So meanwhile, we started making our turn. These guys realized they'd made a mistake, turned around. They're faster than we were, so they started to catch up to us. And at one point, everybody was in the same place. Well, a few seconds later, the fast guys passed us and took off. But right at this point, all of us with different energies caught up with each other. And so this was actually a kind of a visual reflectron. I wish we'd had somebody taking a video of this with a helicopter or something, but it was really quite interesting to watch. Here's the math for anybody who wants it. You can just refer to this if you like, but here's the overall final equation. The time of flight is proportional to all of these things, but the mass is part of that. It's inversely proportional to the square root of the mass. And here's what it looks like as a schematic inside the instrument. On the left, we've got an ion source. This one shows an electrospray ion source, but it really doesn't matter. We're going to break this down piece by piece so you can see what happens, but you've got an ion source, you've got an ion transport region that gets the ions into the vacuum. Then you've got an acceleration region, a reflectron, and a detector, and a couple of pumps just to give you a vacuum. Let's go through this piece by piece. Let's take the ion source first. Again, this shows an electrospray ion source, but you could substitute a dart for this and blow the ions in this way. What's really important here is the atmospheric pressure interface. If you've got ions being formed out here, there's a little orifice into the vacuum system. It's a 400 micron diameter orifice on a cone-shaped ring. This ring out here is pretty close to ground potential and has zero current. So if you don't turn the orifice heater up to a high temperature, you can touch this with your finger. There's absolutely no danger of shock or anything like that. But ions are brought into this region. We have to get them from atmospheric pressure into a high vacuum. So there's a rough pump here. There's a little bit of vacuum pulling the ions in here, and there's also the dart gas blowing the ions into the hull. There are two skimmers in there to define one of the vacuum regions, and they're off-axis. Notice they're not lined up. So the ions can be guided electrostatically to go this way, but the neutrals are just going to come in here and they're going to bump into orifice 2. So you want to trap the contamination if you're analyzing peanut butter carpeting or some kind of material, you don't want to blow that into an ultra-high vacuum region. So we ran DART for about a year the first time, and we found out, we put the electrospray source on one day, and we saw a flicker, and then the signal died. Then we turned it on again, and we saw a flicker, and the signal died. We were baffled. We put the DART back on, it was still working, but we put the electrospray source on, and the signal would die. Well, a flickering signal that dies right away is an indication that there's some charge building up someplace. So we took the atmospheric pressure interface apart and took a look in it, and the back of the orifice was as dark as this thing. It had stalactites and stalagmites dripping off the bottom. We realized we'd really contaminated the interface, but it had done its job, and it kept the inside of the atmospheric pressure interface clean. So behind this, there are a couple of ring lenses in there. That actually just is to collimate a highly charged beam, mostly for electrospray. If you've got lots and lots of charges on each ion, they tend to repel each other, and this just kind of pushes them back into a smaller diameter spot that brings them in. And then you've got an RF ion guide, which is a quadrupole. It's radio frequency only, so it doesn't separate masses like a quadrupole mass spectrometer. It just moves masses from high pressure to low pressure, just kind of contains them and brings them in. But it's a bent RF ion guide, so if you look at it, it's at an angle. That's also to keep the contamination out. The back end of this goes into the high vacuum region, and it's a precision quadrupole. You don't want to get it all gunked up. So bending it this way, at the very least, you might see a tiny film on the opening of the quadrupole, but it won't get very dirty. I've got to hand it to the guys in Japan who designed this. It's a very simple and robust ion source. There are a lot more, atmospheric pressure interface. There are a lot more complicated ones out there. Some systems use a heated capillary, and that works, but it tends to get contaminated. It's much harder to clean. So if you're going to work with real-life samples, which is the real beauty of DART, it's nice to have something that tolerates abuse. Okay, if you use the electrospray source, it's orthogonal. That comes with the system, but that sprays perpendicular to where the ions go in, so all of the spray and salt and everything gets sprayed right down to the bottom. We have a pretty simple interface. There are very few parameters. This region will be one of the two parameters you change on a routine basis. And the fact that everything's off-axis keeps the contamination out of the high vacuum region. Okay, here's our ion transport region. You've got to get the ions from that region into the high vacuum part. And that's a quadrupole ion guide. There are some advantages to this. We don't really accelerate the ions very much until they're high vacuum. If you really give them a high voltage and make them scream through this region, they're going to bump into other gas molecules and break apart. They'll also get scattered and you'll lose ions. So the way this is set up, you don't have a really strong acceleration of the ions until you're in the high vacuum region. There are different kinds of multipole ion guides that you can use. It shows a quadrupole just because it makes you a really small spot size, and having a small spot size helps your resolution. The quadrupole, though, does pass high mass ions and not low mass ions, depending on what voltage you've got. So one of the other parameters is going to be the RF ion guide voltage, which really just tells you how low a mass you can see. And finally, there are some extra lenses in this region right here which help to steer the beam and focus it. Once they're set, you don't worry about them, except very rarely. But you want to make sure the beam is going in straight. Finally, we get into the analyzer where all of this ion preparation becomes important. And there are three regions here. You bring the ions in perpendicular, and then you give them a kick, and you've got this slice of ions going through the reflectron. Let's take a look at it. There's only one reflectron. There are other kinds of reflectrons where they bounce ions more than once through like a W. You can choose different parameters in designing a mass spec. The single reflectron is simple, and you don't have much ion loss. So it's also orthogonal, because when you bring the ions in from the DART, they're moving this way, and you don't want their kinetic energy this way to affect the resolution. But if the ions are analyzed this way, then anything that's happening this way doesn't matter anymore. So orthogonal acceleration is another way to get more ions into the mass spec and to ignore any energy variations in one direction. Here's an animation of sorts. Watch, we'll go through this once or twice. We're going to bring the ions in orthogonally. This whole thing's turned on its side. But then you can watch them being separated and bouncing into the reflectron. So they go through the ion source. They pass a grid. And as they enter here, you shut the voltage behind this and start filling up this region again. These ions get a kick that moves them into the flight tube. And as they start to move down, the low mass ions and the high mass ions start to separate. They might spread out a little bit because they don't have exactly the same energy within each packet. So some of these enter the reflectron. The ones with more energies go deeper, and the ones with less energy go a little less far, and then eventually things catch up at the end. The masses are separated, but the clumps of ions of the same exact mass are focused. And then you start all over again. So let's see, does this go through one more time? No, let's do that, just an animation here. So starting at the beginning, you've got the mixture. Ions fly through and come back. This is done thousands of times per second, and you add up the spectra to get a composite spectrum. So you can run this mass spec at about 10 spectra per second, but each one of those mass spectra is the sum of thousands of individual mass spectra. So if you only have a few ions at a time, you won't have a very good mass spectrum. But if you sum up thousands and thousands of spectra, then you wind up with a pretty good dynamic range, which is the difference between the highest and lowest signal you can measure. Finally, we've got to do something with the information. So the ions hit a detector, and that signal is brought out to the PC. The detector is just a microchannel plate, which is it's a glass disc with thousands of little holes in it. Each hole acts as an electron multiplier. It's actually two microchannel plates back to back at an angle, and that signal then is picked up by an anode and an analog to digital converter and sent to a fast detector. Here's what a microchannel plate looks like. I used to make these things for ITT when I was in college. It's quite a glass-blowing feat. It's really something to see. You imagine just thousands and thousands of little 25 micron ID holes with resolution. They used to be used in night vision goggles. Anyway, the electron strikes the surface and it knocks off another electron. And then that second electron hits the surface and it knocks off another electron. So you get electron multiplication. So one electron in could be about 10 to the 6 electrons coming out the other side. And the reason they've got these two plates back to back is they're staggered at an angle, so an extra electron that just happens to find its way back in won't get a gain of 10 to the 6, because it can never make its way back to the entrance to the first plate. This one must have come from a Japanese slide, because it's got some Japanese on it. Anyway, so finally, we need a data collection system, and there are two ways to do this. There's something called the time-to-digital converter, which is sort of like a super-fast digital stopwatch. That every time an ion hits at a particular time, you count that ion. The other is to make an analog-to-digital converter, which operates really fast, which just takes the whole signal and converts it into a spectrum. We'd like to have high resolution, and you have to have high time resolution, because if you have a resolving power of 6,000, the specification of the Acutoph, the peak width is only 3.5 nanoseconds wide. And you have to be able to continuously collect spectra and have a high duty cycle. And you want to be able to build up the spectrum in real time. If you take these two different detectors, you can compare what they're good for. The time-to-digital converters were used first in a lot of systems, and they're still used in a lot because it's really fast and easy to design. But the premise is there aren't very many ions hitting the detector at a time. So if you've got you're just counting ones or zeros at each time point whether an ion hits the detector or not. The continuous averager, or a fast analog to digital converter, works pretty well, and a spectrum can be accumulated in real time. There's some pros and cons to each of these, but in short, the TDC just has a threshold. So if your signal is above the threshold, it counts 1. If it's below the threshold, it counts 0. And then you just say, at this particular time instant, you've got a signal or not. Here's what happens to the signal as you build it up. So with a time-to-digital converter, which is used in a lot of time of flight still, here's ion 1 hits. So ion 1 hits, it's above the threshold, so you count 1. Ion 2 hits, and it's just off a little bit, but it's in the same bin, so you count 1 for that. Then, let's see, there's another ion. Here's an ion that two ions hit at the same time, but they're only counted as 1. So all of a sudden you're starting to get some distortion in the signal. Or 2 ions hit really fast before the detector has a chance to recover. It still only counts 1 ion. So the problem is the more ion current you've got with a TDC, the more distorted your signal gets. And we like to work with real samples, not just highly dilute samples. So for DART purposes, this isn't a very good way to do things. So you wind up with some skewing of the spectrum, and you have the wrong intensity. So quantitative information is shot, and your peak center is shifted, so exact mass is a mess. Continuous averager, well, I won't go through the schematics here, but it's just fast analog to digital converter. This came along later because it was more complex set of electronics, but electronics get better and better, so this sort of thing becomes more practical. Here's what happens if you have a continuous averager, though, and this does have an influence on the peak shape, so it's worth knowing what this does, and you'll see this when we get in the lab and look at the real peak shapes. What we're doing is taking the actual peak shape, including noise and ringing and things like that, and converting it to a signal that looks just like what the electronics see. So let's see, we're going the wrong way here. Let's back up. Okay, here's the first ion. Here's the next ion. And see, we're actually getting this little bit of ringing because the electronics aren't perfect. There's not a perfect impedance match at the end. So you get a signal and then you get a little recovery time. And that gets figured into the signal. So as we add all this up, we wind up with a correct intensity. The center of the peak is exactly right, but there's just a little bit of tailing and distortion on the end of the peaks that you'll see when you look at the signal. And that comes from the actual electronic noise that's being converted to digital form. But the good news is the peak center will be right and the intensity will match the number of ions. So you can do quantitative analysis with this. Here are the specifications. These are just factory specifications, but the resolving power is 6,000 at mass 609. We tune with electrospray source on. Mass accuracy, they say 5 parts per million with internal reference, but we usually use an external reference. In most cases, we're better than that. I don't know if Bob will be talking about his validation criteria, but you have to decide what you want your performance to be and make sure the instrument matches that before you do any real casework with it. The good news is, after all this complex stuff I've been talking about, there are only 3 parameters you need to know about on a routine basis. When you set the instrument up and install it in the lab, you go through a tuning process, which I do so rarely. I just look it up in the manual and follow the instructions. But when you're in the lab, there are only 3 things we want to think about. One of them is the RF ion guide voltage. Well, let's start with one. One of them is the difference in potential between those 2 skimmers. If it's a small value, the ions just kind of drift through there and they don't break apart. If it's a high value, the ions bump into gas molecules and they break into pieces. So changing that parameter will be important. The RF ion guide voltage, it's called peaks voltage in the software. That's a number that tells you what the RF amplitude is. You just take that number and divide by 10, and that's going to be about the lowest mass you see. So if it's set to 600, the lowest mass you're going to see is about mass 60. If it's set to 1,000, the lowest mass you're going to see is about 100. So that's pretty easy to figure out. And that can be programmed to be switched if you want to see both low and high masses. But basically what will happen is anything above that mass will be detected and anything below that mass won't show up. And finally, the multiplier voltage. You have a voltage on the microchannel plate. Increase it, you get more signal. Decrease it, you get less signal. But you increase it, you also get more noise. You're increasing both signal and noise. So that should be set based on some standard measurements. It's going to be a little different on some of the different systems because some of the mass specs out there have slightly different multipliers in them. But once you find a setting that works, you can pretty much stick with it. Turn the multiplier up too much, your signals are going to go off scale and then you'll get some distortion, and that's something you want to watch out for. So the best thing to do is just to run some standard compounds and make sure everything is giving you reasonable results, and then we're ready to go. I think we're getting down toward the end. Okay, now we've got all this stuff put together. What information do we get out of it? We get exact masses, but we also get isotopic peaks for the mass spectrum. No atom, well, most atoms have more than one isotope. Carbon-12 and carbon-13, and even a trace of carbon-14. All of that information feeds back to be able to give you an elemental composition. We can get fragmentation, and I know Bob will talk more about this, but that will help us to distinguish isomers. You can deliberately break things apart, and some things will break apart just in the process of being ionized. We can get a fingerprint pattern, which is good for material ID. It may not matter exactly what species we're looking at, only that they're reproducible for a given material. And polymers are a good example of that. Want to be able to identify fibers or polymers or paint chips or something like that. If you get a reproducible pattern for that, that's useful in identifying that material. The y-axis of all of this is your ion abundance. That's important for quantitative analysis. There's some things you have to watch out for to get good quantitative analysis, but it certainly can be done. And then there's some other crazy experiments that I'll talk about tomorrow, hydrogen to deuterium exchange, derivatization, and things like that can give you other kinds of information about a sample. Let's take the most important of these here, and I'll do this with an example. Here's a poisonous plant. I was getting ready to go to one of the soft meetings, and I thought it'd be nice to have an example of something that was poisonous. So I went out for a Monday night run, and I skidded past this plant, which I recognized from a plant textbook as being something that was obnoxious. So I grabbed a leaf of this and finished the whole 10K run with holding this leaf in one hand. Got back, stuck it in a vial, and took it in the lab the next morning. Here's the mass spectrum of the leaf, and there are a couple of really strong ions. Well, let's say we didn't know what this is. This is mass 304.154, and there's a peak at 290.174, and there's some other junk in the background. We can treat this as an unknown. I knew what it was, I knew what the plant was, but let's pretend it's an unknown. Well, what do we do with the information? We start with the measured exact mass, and we put some limits on the possible atoms that might be present. You don't expect uranium in the plant, for example, so we'll pick things that are common in organic chemistry, like carbon, hydrogen, oxygen, and nitrogen, and say what possible atoms could combine to give you that exact mass. Then we'll get a list of compositions, and then from that we'll do isotope pattern matching. So we're matching not only the 304.154 peak, but we're also measuring the exact masses and the exact abundances of all the isotopes in that pattern, matching those to the theoretical ones to the measured ones, and then ranking those so that you get a list of compositions. If everything works right, the best match is the correct composition. I'll show you this in the lab, but here's what happens. We run the composition determination for this, and we find out that this has a composition of C17H22NO4. Well, there are many things that could be. If it's a toxin, these are two more common things that it could be. It could be scopolamine, which is an atropine-type alkaloid. I think it's an isomer of atropine, isn't it? Or no. Anyway, it's related. Or it could be cocaine. Well, we can't tell these two apart because they have exactly the same formula if we're just using the exact mass alone. But if we break these things apart and have fragments, then you can tell they're different. Scopolamine should have fragments at mass 138 and 156. Cocaine should have fragments at 182 and 82. The molecules break in these different places. We can do this just by increasing the potential difference in this orifice region. So when you look at the software, it's going to say orifice 1 potential, 20 volts. What that really means, not that this is 20 volts relative to ground, but the difference between this and this is 20 volts. So the ions just have a 20 volt potential traveling through that orifice region. They're just drifting through there gently. They don't bump into gas molecules. They don't break apart very easily. So at 20 volts, you'll get the spectrum that I showed you earlier. If you increase this to say 60 or 90 volts, then the ions get more acceleration in this region. It's a partial vacuum, so they actually get accelerated before they bump into a gas molecule, and then they bump into the gas molecule and they break apart. Then we have fragmentation, and we can distinguish the isomers that way. I just mentioned this in passing that you can also get fragmentation between orifice 2 and the RF ion guide if you set that voltage too high. We don't do things that way. It's better just to set the one parameter. but it could happen back here if you set this difference too high. The software, when it lists a potential here, it means the difference in two successive elements. So orifice 1 potential really means the difference between orifice 1 and orifice 2. The orifice 2 potential really means the difference between orifice 2 and the ring ion guide. It's easier to look at those numbers than it is to look at, absolute voltage relative to ground. Okay, here's a fragment spectrum. We've run the orifice voltage up from 20 volts to 60 volts. Now this stuff starts to break apart, and remember I said scopolamine should have fragments at 138 and 156. Well, there they are. And so that tells me that scopolamine is the most probable assignment for this and not cocaine. You also see there's atropine present, and the fact that both of these are present is also reinforces the fact that this should be scopolamine and not cocaine. But one of the atropine fragments shows up at C8H14N. For contrast, here's cocaine from a dollar bill. This is done at 60 volts again. That should be mass 304.1548. That's a mistake. But the fragments from this one, then you see the 182 and the 82 peaks, just as I was talking about earlier. First time we did this, we were still skeptical, so we swapped a dollar bill and ran GCMS on it. But since then, we found out that there's cocaine on everything if it's ever been circulated. Now, the other thing, this will all come up more in detail throughout the course, but another thing to do is to look for target compounds from a list. And Bob will talk about that, and I'll talk about it. And I know you'll probably talk about this too a little bit. But if you have a list of things that are probably there, you want to know whether they are there or not and get a list of them, you can make an Excel spreadsheet, or you can collect a series of spectra and have software search for which things are present. It will only label those things that are found within an exact mass tolerance. So if it's looking for cocaine, it'll only label it if you find 304.15488 plus or minus, let's say 5 millimass units. And if it's not within that error, it won't label the peak. It's a convenient way to get a survey of things. We use this for looking at antioxidants and polymers, for looking for explosives in a mixture, for looking at drugs and tablets and things like that. Okay, I'm done with this part of the talk. That is the worst of it. I want to get through all the theory and introductions, and this will all make a lot more sense when we get into the lab. But I suppose that's probably a good place to stop and look for questions.
You mentioned the plus or minus 5
millimass units?
Yes. What would give you the fluctuation on the dart?
Well, actually, it's experimentally determined number based on running lots of real samples. And in fact, the instrument specification is better than that. I like to say 5 parts per million or 2 millimass units. But when working with real samples just over the years, I've found that 5 millimass units is a wide enough tolerance that even if there are some interferences there, you can generally get the right composition in the first list. Now, if we only had to rely on that 5 millimass units and we didn't have the isotope matching information, we might get a wrong composition. But it's an experimentally determined number. What will affect that, I guess, is signal to noise. If you've got a really weak signal, it might be hard to find an accurate centroid for it. If you have an unresolved interference, a neighboring peak that isn't completely separated, that's certainly going to affect the mass accuracy. Time of flight is a pretty stable device. In fact, the Acutoph is, I don't know whether it's an accident of design or is intentional, but the flight tube, the thing that affects mass accuracy and time of flight is part per million expansion and contraction of a flight tube with temperature. And because the flight tube is sitting inside the box surrounded by electronics, it's kept at a pretty constant temperature over time, independent of room temperature changes. Now that said, nothing is perfect, and over some period of time you will see some drift in the mass. What I usually do is measure the sample, and then in the same data file, I measure a standard reference compound like polyethylene glycol and use that to calibrate the mass axis and rely on the fact that there's not much drift over that time period. But that said, if you have another known peak in the same spectrum at exactly the same time as the thing you're trying to measure, then that's like a thermometer molecule that can be used to correct the mass axis. So it's best if you can check your spectrum for the presence of known impurities. There's certain known background peaks that we see all the time. There's a silicon peak. It's relatively weak, but it's always there, and it's a nice thing to check somewhere in your background spectrum. And if that falls in exactly the right mass, then you have you have proof that your mass accuracy is good. So that's it pretty much. I mean, interferences, signal to noise, long-term drift of exact mass over time. The one other thing that will affect mass accuracy is if your peak is so strong that it's off scale. Then the peak top will actually be rounded because the actual top of the peak is just beyond the detector limit. And in that case, the software can't calculate the exact centroid of the peak very well, and you'll get an error. But there's usually another indication of that being a problem. One is the peak top is rounded. Two is the isotope peaks are way too strong. So there's some ways to check for error like that. The best thing of all is to run standards, though, and make sure that you get good results on the standard. That way you can validate that the system is working properly. I know Bob's worked out a whole protocol for that he can talk about. The result has to make sense. If it doesn't make sense, then you really should be skeptical.